Okay, perfect. We can see your slides. So let's wait 1 minute at least, and then you will be able to start. Okay, I suppose you can start. So please, screen is yours.
Okay, thank you very much. Good morning, everyone. My name is Tomasz and I'm a student of Silesian University Technology. And today I am pleased to present an article about self-attention generative adversarial networks. Firstly, I want to briefly introduce the article motivation, then present the objectives of this project, shortly present concepts of generative adversarial networks. Next, I will present the modified architecture, present the dataset that was used to work on this project, and the results that were obtained. Generating synthetic images such as faces, like medical images such as X-rays or CT scans, or biometrics has become an increasingly important topic. This is due to the numerous opportunities and challenges associated with the applications of networks that enable such generation. The goal is to build a network that could replicate reality as accurately as possible, which is inherently a challenging task. One promising solution is generative adversarial networks, which allow for the generation of images, photos, or text from real data. To further improve the quality and efficiency of these networks, a self-attention mechanism was integrated into the architecture. The primary objectives for the project were as follows: to prepare a network that is more resistant to generating artifacts, and it is very crucial in medical applications where such artifacts can disrupt the accurate classification, which is critical for patients' diagnosis and treatment. And the second one was to enhance the stability of the generation process. This is crucial due to inherent challenges in training, where instability can lead to poor results, inefficiency, and there would be no convergence. And the last one was to achieve a high quality result with fewer training epochs. Most GNS require tens of thousands of epochs to produce realistic outputs, so the goal was to improve the efficiency. Generative adversarial networks were introduced by Ian Goodfellow and his colleagues in 2014. GNS consists of two main components, a generator and a discriminator. These two neural networks are trained simultaneously in adversarial manner. Based on random input, generator creates synthetic data samples, such as images, by learning from a training dataset. And its goal is to produce data that is indistinguishable from the real world. Discriminator evaluates the samples and attempts to distinguish between real data from the training set and fake data produced by the generator. During the training process, the generator improves its ability to identify fake data, and generator improves its ability to generate fake data, and the discriminator enhances its ability to identify it. The adversarial loss function guides both networks towards generating high-quality, realistic data. And the loss function used in generative adversarial networks in general is defined as follows: minimize over G, maximize over D. V of D and G equals the expectation with respect to X sampled from P data of X of log D of X plus the expectation with respect to Z sampled from P data of Z of log 1 minus D of G of Z. In this context, G of Z is the generator and D of X is the discriminator. The discriminator D of X tries to maximize the function V of D and G, while the generator G of Z minimizes this function, leading to min-max relationship. The self-attention model or attention mechanism significantly enhances GANs by improving their ability to generate high-quality and contextually coherent data. The self-attention mechanism works as follows. Each input feature is transformed into three vectors, a query Q, a key T, and a value V. These vectors are obtained through learned linear transformations. The attention scores are computed by taking the dot product of the query vector with all key vectors, followed by a softmax operation to normalize these scores. This results in weights that represents the importance of each feature relative to others. Each value vector is then weighted by its corresponding attention score, and a weighted sum is calculated. This sum represents the output of the self-attention layer, capturing dependencies across different regions of the input. In the presented architecture, the self-attention model is integrated into both the generator and discriminator networks. This integration allows the generator to produce images with fine-grained details and coherent structures by understanding the relationships between distant pixels. Similarly, the discriminator becomes more effective at distinguishing real images from the generated ones by considering the global context by the image. The dataset used in this project consists in 202,599 face images of celebrities. Each one is 178 by 178 pixel size, and it is prepared by researchers at the Chinese University of Hong Kong. The dataset was divided into a training and test set in 80% to 20% ratio. Despite the relatively small number of epochs, the network generated samples of realistic-looking faces and only in a few cases generated artifacts, which can be seen on the slide. The FID metric, or fractured inception distance, was adopted for comparison with another generative adversarial networks. This metric reliably assesses both the visual fidelity and diversity of generated samples, and lower FID scores indicated better performance. The proposed architecture achieved a score of 2188, which is better than DGen CS and PRBGN, which have FID scores of 34.13 and 22.45 respectively. The self-attention generative adversarial networks improve both the accuracy of generated images and provides greater stability, reducing the likelihood of mode collapse, where the generator becomes stuck in generating nearly identical data samples, thereby hindering the improvement of overall quality and diversity in generated outputs. Future research should focus on reducing the amount of data needed for generation, which is particularly important for medical data where data availability can be limited. Additionally, further studies should address solutions to defend against attacks such as biometric spoofing that exploit these networks. There are also some ethical concerns about GANs that need to be addressed, especially to generate feedbacks. That's all for today. Thank you for your attention.
Thank you very much for your presentation. You're practically right on time, so thank you for that also. You